Yes, hello everyone. Today I'll be summarizing the core concept of the control law design for full state feedback based on the provided materials. The overall goal of this state space design method is to create a robust control law. This process typically involves key steps for we design the control law and we design estimator and which is crucial because in real systems we often can't know or our internal states, so we combine the control law and the estimator. And finally, we introduce a reference input so the system can follow target. The foundational concept is full state feedback. This begins with an important though often unrealistic assumption that we have access to all elements of the state vector x. So given the unrealistic assumption, we define our control input u is minus kx and x dot is ax plus bu. So x dot is a minus bkx. So that the eigenvalue of this new a minus bk matrix, which are the closed loop force, are placed in the desired locations. This location determines the stability and response characteristic of our control system. So the document outlines three main ways to find the gain k. So first, direct coefficient matching as shown in the pendulum example. We calculate determinant si minus a minus bk, so which result in a polynomial with k gains. We then compare it to the desired polynomial and solve for the k values. And the second is transform the system A, comma B into the canonical form AC, comma BC. So using a transformation X is TG. So solve the for the gains KC in this simpler form. Transform the gain back to the original. K is KX T inverse matrix. And third and the most direct is Ekman's formula. This single equation K is 0, 0, 0, 0 last one C inverse matrix and alpha CA. So where C is con and the C condition is controllability matrix. So alpha is alpha I are the coefficients of the desired characteristic equations. So this brings us to the critical condition. We can only shift the fault to any desired location if and only if the system is controllable. So far, our controller is U is minus KX, is just a regulator designed to drive the system state to zero. But what if we want to trigger non-zero reference R? So simple attempt like U is minus KX plus R will almost surely result in a non-zero steady state error. So our goal is zero steady state zero. So meaning the output YSS must equal the input R. And so the state value is state XSS and the input USS. So these are scaled version of R and SXS is NXR and USS is NUR. NS and NU is matrix equation derived from the steady state system equations. The document shows two ways to implement. There's a robust method is U is USS minus KSS X minus XXS. So a more common form is to combine the gains into single freak scaling factor m bar, giving the final control law minus kx plus m bar is u. And this m bar is calculated as m bar is nu plus knx. The plot for the pendulum example show this works as I correctly track the reference input is 1. In conclusion, we cover two key parts of state space design. First, using full state feedback u is minus kx to arbitrarily place the closed loop force, which is possible only if the system is controllable. And second, introducing a reference input using steady state gains to create a final control. Rho u is minus kx plus m bar r that achieves zero steady state error for tracking. The next logical step, as noted at the beginning, would be to design an estimator for the practical cases where we cannot measure the full state. Thank you.